Hi everyone, welcome to this seminar. It's going to be an interesting tale of computer vision that we will go through in this one. Briefly introducing myself, I'm Alok Govil. I'm a principal engineer working at Amazon based out of India. So with that, we'll just get started with this interesting tale of computer vision. So what we have is there are a lot of these superheroes and there are already so many of them and there are more and more who are applying to become superheroes. So believe it or not, there are 10,000 applications from humans trying to be superhero every single week. So it's getting hard to know who's who. And in the meanwhile, what's also going on is that some of these bad people, right? They're also trying to apply for superheroes just so that they can get into the club and get some insider information. So what they decide to do, what the superheroes decide to do, is to do identity verification on these on all these new applications which are coming in. So they want to check the ID. They ask this a computer called named Vision to do this job. So this computer named Vision, he's computer in itself, but he doesn't actually know how he himself works. So he goes on, he finds out there's a team at Amazon who's doing something similar. So he approaches with them. And when he talks to them, he finds out he was very welcomed by the team, but the team asked computer vision, do you know computer vision and machine learning? But this computer is surprised because first off, he is computer vision. So what does he know? What does it mean that he knows computer vision? And then he does not know any machine name learning. So that's another surprise for him. So he learns from these people at Amazon that computer vision and machine learning are two branches of computer science which can be used to automate these things like he's been asked to do, which is reviewing 10,000 applications every week. So computer vision thought, what the heck? He doesn't know all these two things to be there, but he'll just figure. So he started firing up Microsoft Excel and he did something with it, and we'll just see what exactly computer vision did. So with that, we are in Microsoft Excel. So here's a sample image that we have built. Obviously, this one is a fake one. This Mona Lisa image and the sample passport is all just this not a real one. And the core reason why we created the story and we chose this image about ID documents is because what we have in this single image are lines, corners, face, as well as some text. And what we are going to do in this session, interestingly, we will see some algorithms for detecting lines, corners, face, and text right within Excel. And that will be done using plain old one-liner Excel formulas. There is no scripts used, no third-party calls made. It will all happen right here in Excel. So we'll get started to see how that happens. So first off, some of you may know, but some of you may not. What we have is that any image is just two-dimensional array of pixel values. So as an example, in this particular image, what you see is that the very top left pixel has the value of red, green, and blue respectively at 217, 217, and 218. Likewise, all pixels have these RGB values, and the way these values work is that a value of 255 will represent the full on color primary, which could be red, green, or blue. And a value of 0 means that primary is totally dark, which we would call it as black. So what that means is that a color which is full on red, like that sample passport text that's written here, that would have a value of 255 for red and 0 for green and blue. Likewise, yellow becomes a mixture of red and green, so it becomes 255, 255, 0. So an image just becomes, the way we see with our eyes, we don't realize, but an image for a machine is just a 2D array of these numbers. We won't talk about how do we read an image file, but I show some sample code that you could fairly easily use. This is shown for Java, but pretty much any language would come with some API to be able to read some image given a file. And then you can go on to find its height, width, and you can read all pixel values. Now, what you can do with that is that once you have read the data of the image into memory, you can save it very readily into a CSV file. CSV stands for comma separated values. It is just values separated by commas, one row of an image put into each line, and Excel readily opens with that. You can read this article for more about how this is being done, but we'll skip that for here. So what we have done with that is that we try to show what exactly this image looks like. We just read off the green channel of that image, just the green. Red and blue were ignored. Just the data for the green channel of that image using this CSV file technique into Excel. And you see that 217 value using what you saw here show up basically right here. This 217 value, 217 in these values, they are showing up basically right here. So we have this entire data loaded into this sheet, which has formatted by changing rows and widths to make them look like squares. Now we'll look at one very neat feature in Microsoft Excel, which is called color scales. So you can see this data is loaded in Excel here. What you can do is you can go to this conditional formatting. You can assign different data bars. You can see live how it is changing. You can assign these different color scales. You can specify these icons and so on. So all that data could be assigned like that. And so what we have done here is that we assigned a custom color scale to them, which is looking like this. So if you again basically see here, you'll be able to see grayscales assigned to it with 0 value corresponding to black and 255 correspond to full on white. So what that does is that the green channel in the original image that we had goes on to look like grayscales. As you can see here, a value of 242 is brighter. And these values, which are probably smaller, or value of 12 here, that ends up looking darker. So let's look at, if we apply this color scale to our entire data, what does it look like? So this tab shows that. So what you're seeing here is the very same data. You can see nothing has changed. It's just that the colors have these gray scales have appeared. And the values which are smaller, say this 110, that is a darker cell compared to this value which is 206, which is a little brighter cell. So you assign this grayscale value to all the data in our sheet, and now we are going to do a very neat trick. What we will do is we will just zoom out on this sheet. So as you see, as we are zooming out, numbers keep on becoming smaller. At some point in time, the numbers actually go on to disappear. I'm not sure whether that's by design or that's by purpose, but Excel stops drawing fonts at that point in time, but the colors, the shades we assign to all the cells still shows up. And as a result of that, we start seeing the image that we had, just the green channel of it, but seen as a grayscale, right within Excel. That's a neat trick that we are going to use, and we'll proceed with it from that. Now notice that this image is just an object embedded into Excel. We can't do anything with it, while this one is not an image, it's an Excel sheet. As you can see, the value of the A1 cell, top left cell, is still showing up. You can move around this to any basically cell. It's a tiny dot that you can really see here moving around. That's our cell, and the value of it shows up basically right here. So with that, what this will now allow us to do is to start doing mathematical operations on these cell values. And simultaneously, we'll be able to visualize what that image looks like right here. We don't have to do anything for it. We'll apply some formulas and we'll see what happens with that. So let's just get started with it. So as a warm-up, the very simple thing we have done is this one. So what, as you see in the formula, is done is taking every cell in that original image. And IMG column, IMG hyphen is referring to this particular sheet. So it's taking every cell in that sheet and it's multiplying that by 0.7. So as you might imagine, what multiplying each one of those values by 0.7 does is that a value of black, which was, as you call, 0, stays 0. So black stays black. But a value of 255, which was full on white, will end up becoming something smaller, i.e., as I recall, I think it's around 185. And so it takes a grayscale value instead of remaining full on bright. So you can see going from here to there, this original image to this darker one, our image has become darker. So just by multiplying those values, we got this result and we can visualize it right here. Again, this is also an Excel sheet. This is not like an actual image. We'll now keep on building like this, trying single one-liner like formulas and see some basically magic like keep on happening. So let's now look at what if we apply an if formula to it. Here what we are doing is very similar. It says if the image cell value is more than 160, then force the value to be 255, else make it 0. So what then happens is that any time in our original image, the value is brighter than the grayscale value of 160, it becomes white. While if it is darker, as you can see around Mona Lisa's like here, that's darker value, it becomes full on black. So you see, like very simple operation. We turn now a grayscale image to a like binary image. And one way in which this operation is very useful is for doing optical character recognition, which is OCR. OCR is used to the viewer to read the text where a background or the actual shade of gray of the text is not interesting for us. We just want to look at what the text looks like. Now, some of you may be curious, where did we get this value of 160 from? Here, this was chosen just by trial and error, but there are algorithms to choose it automatically also. In fact, there are algorithms that commonly choose this value differently for different cells based on the brightness level in the local region. So what we will now do next is we will look at another operation. So far what we have done, we took the pixel values themselves with the original image and we modified the corresponding value of the image from those like cells. Now what we will do is we'll do some local operations which go from one pixel to beyond. Let's see what exactly that means. So if we look at this value here in this yellow cell here, that is now average of this 5 by 5 grid of cells over like here. So we can actually like see, we can go on to click this cell. And if I press F2, you basically see this particular value here is the average of these particular like cells. Of course, we are using the same formula like everywhere. So that's why like this cell would be an average of these values and so on. Now, Excel also has one simplification. If there is no value, it ignores them from the average. So that's why we don't have to do anything for this value, which is actually the average of like these cells. So it's already like taken care of. Nothing needs to be done. So now that we have basically done that, let's see what actually this average operation is doing. Right? So if you look at like some values like here, especially around these like corners, the everything results in this blurring like happen. Why? The value of this cell, right? Say we give this one, which is these cells, and these cells, they're not very different. They are very just different by like one little row. So there's this smoothness that's like happens like that. So what we've seen is a blurring operation that has happened. So let us see what happens if we apply the same operation to the entire image. We just look at our original image. This is what it looked like. And now we look at the blurred version like of it. So you can see very clearly it's like gotten blurred. So all we had to do, as you can see here, any cell here, you look at its average of those like grid of the cells. That's all there is, right? And our image basically got blurred. So with that like warm-up completed, let's now look at how do we use these techniques to find edges and lines in the image. Then we will work our way to finding corners. Then we'll show a demonstration of how a face detection algorithm like works. And finally, again, we'll show a demonstration of how to read text in an image, which is OCR. So far what we saw was interesting, right? What we had was, we started with the original image, and we applied this average operation, which is summing the values in the local neighborhood and then dividing by n to compute this average. And that resulted in blurring. Now, what we want to do instead is that what we want to sharpen things in the image, not like blur them. So let us look at how we might actually do that. So remember in the previous image, we took a 3 by 5 by 5 grid. Here I'm just taking 3 by 3. Right? We were averaging that value. So what we're going to do here instead is that instead of averaging, which is like just summing those like 9 values in this scenario, we introduce a negative sign because we want to do some subtraction. Remember, we are going from blurring, which had only the plus operations, towards sharpening. We want to do reverse of it. So that's why we introduce these negative signs. So look briefly at like how exactly this is like working. So all we are doing here, we are taking these values, 3 by 3 grid you see here, we are multiplying those 3 by 3 values with these respective values in this mask. So this value, which is 182, is being multiplied by -1. This value, which is 180, is being multiplied by -2. Likewise for all 9 values. Once we have computed these like pairwise multiplications, we just add it together, right? So essentially it's a weighted sum. We are taking this 3 by 3 grid of these pixel values, the grayscales, and multiplying these, we are computing weighted sum with that. And resulting values showing up in this cell. You might see, I'll put basically this, like you can see the formula here is exactly that. There's nothing more to see there. You can see it's taking these values, it's multiplying them by those respective coefficients, and it's just putting basically that weighted sum here. So here's what happens now. If you look at cell like this, right, which is taking these values, the values on the left and the values on the right are roughly equal. You see, these are like very similar shades of light gray. Now, what happens when the values on the left and right are equal? Because these coefficients are equal and opposite, that results in the values here coming out as small. But we will see what happens on a cell like this one. Right? Here, what you see is the values on the left side are these larger values because they are grayscales, and the values on this side are smaller values because they are darker. Right? When we do pairwise multiplication with these, we see a lot more negative values coming out than positive values coming out. So net result is what we see here is a hugely negative value. In this case, as I can tell, is -538. Right? You go on the other side, exactly the reverse happens. The negative values are getting multiplied by smaller values, while these positive ones are getting multiplied by larger values. So that results in hugely positive value. So since we have both negatives and positives, we have chosen different color scales here. So negative values become red, positive become green, and the smaller values become white. Now, question is, we understand why we choose negative values here and positive values here. Of course, we have flipped those around also. That would not have resulted in anything except for these signs here like so. But why did we choose 1, 2, and 1 along the vertical? So see what we are trying to say do, if you look at a value which is like this one, right? Or maybe say this one, right? So you see these values here are brighter, here is a little bit darker. But the values in the corresponding rows are roughly like equal. So that results in still some cancellation happen. So on these horizontal edges. So what we are seeing is when we have vertical edges, this operation goes on to spot them and enhances them. Same thing on this side. But on the horizontal edges, what we are doing instead, we don't have minuses here and pluses here. We are rather having the same sign along the vertical, which actually results in blurring across the horizontal or along the vertical. So that blurring across the vertical is making those horizontal edges disappear and do, while these other vertical edges are sharpening. So let's look at what happens when we apply the same operation to the entire image. We had this original image, and we apply this operation to the entire image and see what has happened. So again, we have to choose a different color scales here. It's not red and green like anymore. So 0 values are this gray level of 128. Negative values are showing up in blacks, and positive values are showing up in these whites. So what you're seeing here is that the horizontal edge of this like passport document here is disappeared. This edge of it is appearing darker, probably because the like gradient is going from darker here to brighter to darker, and here is reverting from darker to brighter. So that's what we actually end up seeing here. There are 2 vertical edges like which are prominent, like becoming sharper. One is this one, which is going from brighter side to darker side, so resulting in a negative values here, and positive values on this like other side. Similar thing are happening like here, around here, and like so on. So with that, we saw how do we find vertical edges. What if we want to find horizontal edges? Of course, the trick is fairly simple. We just rotate this mask, right? So in this case, we previously we had -1, 0, -1 here. Sorry, -1, 2, -1 here, but now we rotated that 90 degrees. We could have easily rotated the 90 degrees other way also, that we just flip the signs, nothing else would like happen. So we take the same mask and we apply on the entire image again, original entire image, and see what happens now. This time we have found these horizontal edges, we have sharpened them. While the vertical edges, something like these ones, have gone. So we'll flip back and forth between those vertical ones and you'll see the contrast very clearly. See how they're looking? Awesome. So far what we had, we found these horizontal and vertical edges. But what if we want to find edges along all different directions? At 45 degrees, 39 degrees, so many of them. So how do we basically go on to do? Well, you might think of like trying to rotate this matrix we saw, 45 degrees, yeah, it can work. 39 degrees, a little bit harder. But there's a simple technique that actually works out. We know basically there that I called this like gradient mask, and it called like gradient because this is approximating a gradient, which is the derivative along y direction and x direction. So it turns out to find gradient across any direction or magnitude of it, all you have to do is to take those vertical gradients and horizontal gradients and compute their RMS values. RMS stands for root mean square. So we took that vertical image, we square it. We took that horizontal image, we square it. We sum, we compute square root. That's our like output. So with that, very simple formula is you should be able to see right here. You just square obviously those like values there. That's all. That's all there is. So interestingly, it turns out just by doing this, as far as the gradient approximation that we made is good enough, this should find very nice like edges. So let's see what happens if we apply this to entire image. Notice this time we are not referring to the original IMG image. We are referring to these vertical, this sheet, and horizontal, two edges we had like found. Applying the same formula, and you see it has found edges on all basically directions. I like you to pay attention to basically this original image again. Look around like Mona Lisa's like here. It's almost like circle. And now when we look at this particular like image, where is this? There you go. What you see is it's found basically very smooth line here, right? So it's not that along 45 degrees is doing something else, along vertical is doing something else. In fact, if you were to have like some sort of like circle in the original image, it's gonna find nearly like smooth basically circle along the side. So the RMS value is taking basically that is like working fairly well. We still have these like edges of this horizontal and vertical both showing up. They look a little bit darker, so maybe compression of like video basically hides them, but they are still there. So here's what we are going to do next. What we will have is we already looked at this binarization operation. We'll do that again on this edge image. So let's see what it looks like. So what we have done here is we use a threshold of like 30, smaller compared to what we did last time around. And we did that so that we retain these like horizontal and vertical edges, which are the borders of this like passport. So the value of 30 here is chosen by again hit and try, looking at those specific values. But what you see here is that we have found all of basically those like edges, including some of these like horizontal lines, some should be around text like also. So with that, we see how, right, in Excel, by using these like simple formulas, we found edges in the image. But for the machine, this is still just an Excel sheet. You can in fact like zoom in, right, and you'll start seeing some values, ones and zeros in this case. Our machine still does not know where's what. Probably it will never, but we'll try to do something more with it. So here's what we are like missing right now. So let us say we were having an image like this. Obviously, we know the two sides of the road are actually like parallel, roughly parallel, right? But in the image, they seem to be converging towards this horizon, right? So in the coordinate system of the image, these are not parallel lines, but in the world coordinate system, which is the real world thing, those are like parallel lines. So what we want to do is we found basically these like edges, but what we want to be able to find equations of those lines there. So what exactly is this like line looking like, which our machine still does not know, because for it it's just a 2D array of like values. So how do we find those equations such that we can now then go on to use those equations, map them, translate them from say knowing the orientation of the camera. We could map them from the coordinate system of the camera to the coordinate system of the world, just as an example. So we'll see how exactly we'll do that. It's again a very simple technique that we'll apply. What we'll do is voting for lines. So let's see what basically that looks like. So what we have done is we assign the center of the image as coordinate 0, 0. That's our origin. For that, we parameterize a line in polar coordinates. That is, we define a line by the normal, this one, which is done at an angle of like theta, and at a distance of like r. Right? So each r theta pair goes on to define that line, which is normal to basically that like line from the origin. Right? The equation of this line becomes simple now. It's x cos theta plus y sin theta equals r. So with that, we can consider any line passing through this image. So try to take a guess at what range we would have to choose for theta and likewise for r, so that we have every single line that we could pass through this image. So for theta, we can either make it go down from 0 degrees to 360 degrees, which is in radians 0 to pi, or we can make it go from say minus pi by 2 to plus pi by 2 equal, same things. We can go to make the r go from most extreme point, which would be along the diagonal, right, to that opposite diagonal. So we can choose the value going from say minus basically this value to plus this value, and so on, right? So that's what we have basically done. So let's see what exactly is going on. So we have now two sheets in Excel. First one has these theta values, which are going from minus pi by 2 to plus pi by 2, changing along the horizontal, while along the vertical is exactly the same values. Right, you see the same value here, same value here, same value, but along the horizontal is changing. If you scroll to the other side of it, you'll see like opposite value to basically that. Similarly, we have created a sheet for r, radius. This is going from minus 200 to plus 200, but is going changing along the vertical. Along the horizontal is exactly the same values. So notice the trick we have here. Theta and r, they are going along across different axes. So here's what this means. So if I go on to say cell J11, right, I see some theta value, and I correspondingly go to cell J11 on this theta sheet also, right here. We also basically get some R value. And since they are going across two different like axes, right, by going across all of these cells in the 2D arrays, we choose a range of theta values and a range of R values. Of course, the values of both are discrete. So we are basically looking at discrete like lines, set of lines only. It's not infinite like set of lines for all R values and all theta values. So what we will do now is this. So consider this line, which is like defined by R and theta, and we have the R and theta pairs which are going through a line like this, a line horizontal line, a vertical line, all of those passing through this image. Now, what we want to do is we're going to look at this H binarized image, this one. Now, imagine our line is going something like this, right? But I'll refer to basically this one here only, right? So each time an edge falls on that line, so you see basically there's a like line which is roughly going through here. Each time an edge falls on that particular line, that line will get a vote of 1. While in these areas where there's no edge, it's all black, there's no vote coming to it. Obviously, the line does not get a vote from an edge here, which is not even falling on the line. Only along with this particular line, we look at how many pixels are bright in this edge binarized like image. Simple. So that's what we do. We are doing just this like voting, and this particular sheet takes some time to compute on this particular machine, 20 to 30 minutes, because the system is like not optimized, even though Excel does fairly well on it. With that, our voting is complete, but let's look at this formula a little bit to see what's going on. So what you're seeing here is, again, x cos theta plus y sin theta minus r. Right? If that value is less than 0.5 in magnitude, that means the actual edge point is fairly within half a pixel of that line. Right? So this basically tells, this particular thing tells, hey, that edge pixel is on the line. In the same way, we use that value of the edge itself, if that is 1, only then this thing is taken into account because we are doing a product like here. Right? So product of this thing, first thing tells is like falling on the line. Second thing says it's an edge over there. So product of those two means both of those things are true together. And then we have a sum which does the voting across that line. So here's what the result comes. Keep in mind we have R and theta axis like defined. So what we see here is these vote counts appearing. You can go to a specific given cell and like see its like value. And you'll see basically what that vote count is looking like. we have like three different types of areas here. Some areas are like here, which are like very dark, where barely like for those R and theta values, there are barely any edge pixels showing on them. Then there are areas like this, which are quite like gray, where they are receiving a lot of like vote count. Right? There's a lot of votes coming to because there are edge pixels falling on them. But curiously, if we were to move around those R and theta, if we move a little bit around, the vote count does not really change. That is to say, if we are changing the R, we're changing the sorry, R would be changed like this, theta changing like this. Still, a lot of like pixels are falling on it. Let's now look at like areas like this. This is interesting. Here we have a large vote count for some given like R and theta. But if we were to change R, we move it around, or theta, vote count suddenly like drops. So if you were to look at like this image, that's what is going on. We have a lot of this text area, this photo area, a line going through with these like regions. We'll see some vote count coming in, but as you rotate with those lines, not much changes. But on the other hand, when you're looking at an edge like this, right, you have some given R and theta. Like moment you will change those R and theta, vote count dips sharply. So that is what is like going on here. So those points are of our interest to us. These ones, the ones which are like standing out on themselves. You see a lot of them coming out. Right? So here's the trick we use to isolate them now. So remember, we have to remove three types of things. One of these darker regions will need some condition for that. We have to remove these like gray regions. We have to use some condition for that. And we have to find out these ones. So we have to use a condition for that. So that's exactly what we're going to do here. So there are three techniques here which are being applied. One, it says the value here is more than equals 150. So any value where vote count is less than that, right, is taken out. So darker regions that we had go away. Of course, that threshold value is chosen by handcrafting here, but there are algorithms to do that too. Second logic that we have is that if the value here is more than or equals to the local neighborhood, the maximum of the local neighborhood, we keep it. Otherwise, we force it 0. So see what will like happen here. Right? If we go back to this sheet, around a point like this, there are a lot of these like local region also seeing some grayscale values. But if those values are smaller, they will be forced to like 0. So in any local neighborhood, we suppress basically the non-maximal like values. That's why this operation is called non-maximal suppression, even though we have tweaked it to subtract these like gray areas like also. And the third region is looking at trying to subtract those gray areas. All it basically says is that if the average versus the max has basically some particular ratio, then basically we keep, otherwise we remove. So with those three like operations like ANDed together, right? We have these like interesting points remaining. These ones, we see some spurious points here, for which I'm not going to talk about those like here, but I'll show you some references to explain why they are like appearing. So we have these points here. So you can really see we'll switch back and forth between these sheets. So this point here and these points here, they are all basically like showing up here. We found these like interesting points, right? And their locations tell us R and theta respectively. Right? How? Well, if I go to this point, that cell is FD48. FD48 in this theta and R give me the respectively R and theta like values. So with those interesting trick, what we have done, we took these image and just by voting across those R and theta, we have found basically those interesting like edges which are falling along those lines, but they're still in this like image. Now, assuming like people know how to read simple arrays, it's not too hard for us to like read the coordinates of these points just by going step by step on all of these basically R and theta values, and we can see where the values are 1. And we make sure to ignore this spurious point that show up at plus minus 45 degrees like angles. So what I've done next, this is actually the only thing in this sheet which is not running entirely with formulas. I read those like location of these points manually, and I placed those like rows and column values right here. Right, so those coordinates basically of these pixels are really showing up here, and with those at those particular like values, we can read off those R and theta like values where these interesting points are, and we can even go on to that hub sheet. Remember, this sheet particular one is named hub because it's like named after hub transform, the person who I believe invented it, the algorithm. So from this sheet, we actually get the vote counts to like 2. So that's what we like have here. We have R and theta values and the vote count. And our line equation is still very simple, same thing as before. X cos theta plus y sin theta equals R. You plug in the values of R and theta, and that gives you an equation of the form AX plus BY equals C, which is an equation of a line. Right? So for each one of these like values, I think we have some 14 like lines here based on the threshold we chose. That gives us 14 interesting lines which we have like found. So how do we still know what those lines are? We are not draw them. We are not trying to get them superimposed on the original image. So let's see how we could actually do that. Now, it could be fairly easy to write some algorithm basically for it. There's in fact some popular algorithm, as I recall, called Bresnan algorithm for doing that. But we are going to do this in Excel. We are not using any scripts or anything. We're just using plain old formulas. So let's see how we could do exactly that. Okay, so all we are really doing here, we again put the same equation, x cos theta plus y sin theta minus r less than 0.5. That means we see that particular value is within half a pixel like of it. Right? And we again multiply by, I don't recall exactly what I'm doing here, but basically I sum them. What sum is actually doing is that it's summing across different lines here. Remember we had 14 lines. If any one of those like values, right, is more than 1, which means it lies on at least like one of those lines, then the value becomes 1, otherwise it becomes 0. So see what has happened? Just by that simple formula pasted everywhere, we just got our lines like drawn up right there. So let us see basically what those lines look like now, right? When we superimpose those on the original image. So here what we have done is, remember that image we already like had, we multiplied by 1 minus lines. That's because we flipped the color. What was like bright here, 1, right? I wanted it black, and vice versa. So we flipped it here by doing 1 minus that, and we multiplied. And you can see those lines are showing up on the top of our image. And right within Excel, we have found those interesting like edges. Hub transform algorithm implemented right in Excel. Again, as you can see, this is Excel sheet. Even those line drawings are Excel sheets, right? It's just the pixel values there. There's no formula, nothing, no formula used to like draw these like no built-in formula in Excel to draw basically those lines, right? And we have not made any third-party API call, nothing. It's just plain old numbers manipulated to get this done. So now that we have like found those lines, we'll proceed. I think we are like a little bit falling behind time, so we'll speed up a little bit. So this section I will like tend to speed up a little bit. This image also includes some math, so we'll basically like skip that. But all these materials, this entire Excel sheet has been open sourced by Amazon, thanks to Amazon. So it is available to all of you to like play around with it. I'll quickly zip through this corner detection like pieces. So first we want to define what exactly is a like corner. So these flat areas in an image or these like edge areas that we've already found, we want to like ignore those. What we call key points or corners are areas like this, where there's some activity going around in the neighborhood of a point in at least two dimensions, because it's a 2D like image. Here there's activity going on, which is along one dimension only. Here there's no activity going on. So to do that, what we have is, we already found basically these like vert and horizontal images that we've seen before. We try to model the local neighborhood around basically those in terms of an ellipse. Right? So we look at this lambda max and lambda min values, right? And these values are defined by very simple formulas. I'm not going to like details like of it, right? But we'll compute this lambda min value. So if lambda min value has some like some particular like value size, like it's more than some like threshold, positive or negative, but positive only, right? That would mean there's activity along second dimension also. So edge as well as like flat areas will like go away. Right? Computing this is fairly easy. We already had this vert image. We computed basically that. So that's what is showing up here. Is the square of it applied everywhere. Horizontal image, again, basically square of that like applied here. And we are also doing this sigma. So we are blurring in the local neighborhood. So squared and blurred, squared and blurred. And likewise, those two things multiplied together and then again blurred. So with that, we have these three formulas like computed, the inside of it, and we just have to compute lambda min. And that also becomes very simple to like compute. So you can see that lambda min formula, again, a one-liner formula appearing here, and that gets rid of like all these like edges and lines, and some of these interesting red features now remain. So what we're still interested in is looking at these peaks of these like red regions. So we want to again take the maximum values and get rid of those like local neighborhood around. But that's something we have already seen. It's not too hard. We applied a similar like technique before, and we see these like points make an appearance. So these points basically like are here, but what exactly are those points? Well, we can just try superimposing them again on the top of the original image, and we start seeing it as found interesting like good things. So we see some four corners of the image. We see basically these like edges like corners are showing up here. Similarly, some points around like text. So all of those interesting points we found again using some very simple like formulation. However, for the computer, all these points are alike. Right? This point, they are not any different. So one popular technique in computer vision is called descriptors, where in the you can read more about basically that in very excellent like blog by Gil here. And this one describes how you can go around those corners and find some sort of like local signatures of like those points around each visible of those points, such that we can distinguish one type of point from like another. So the edge basically type here may match another edge which is of similar like shape, but it may not match a point basically which may be looking at it, this corner of a T. Right? So using these descriptors and then doing some key point matching, a very large number of like algorithms can work. That can include reverse image search. It can map one image taken to another image, which may be like aligned, which is called image registration. And using that image registration, if there's a video going on which is like shaky, you can actually go on to stabilize that video. So that's all we'll do for corner detection. You can play around with this Excel sheet and as well as read some of these links to like look at more. Now we will look at how do we do a demo of like how a face can be found. Starting to get interesting, and it's all going to happen right within Excel. So let's look at the original image again. So what we want to do is to locate Mona Lisa's like face here. We have another shadow face looking here. We will tend to like ignore it for the time being. So we'll just find this Mona Lisa's face. So there's a technique called, there's something called like Haar features, which was used for face detection by this landmark paper by Viola and Jones. You can read the actual like paper here. So what it does, the key insight that was to be done was to say, hey, in a face, any human face, the region around the eyes tends to look darker than the forehead and this like cheeks region. And the regions around the nose tends to also look like brighter than the region around the eyes region. In fact, this thing tends to apply irrespective of the skin tones of the people. Right? But we will see like how later different skin tones are handled. For now, we'll just assume like this particular like face. And what we see here is that the eyes region is darker than forehead and cheeks. Likewise, this nose area is brighter than these areas here. So that's what we want to do. We want to look at basically these two like type of region there. We're going to see the pixel values in this region are bright enough compared to the pixel values in these regions. Similarly for here. So that's all we are going to do. So how do we compute that? It's really simple. I took an extract of the Mona Lisa image, it's zoomed in. So let's look at this formula like here. Right? What you see is it's taking these regions, it's multiplying them by, it's averaging them, all those values, subtracting them out, while this top and bottom regions are also like average, but they are on the positive side. Right? So that's all basically the formula here is doing. Right? Let's apply that formula everywhere on our original image, and we see some values appear. Most of them are dark, but we see some of these like gray regions like appear. So these are the regions where we are seeing that region of basically like this type. What we saw here, these two regions tend to be brighter than on an average than this region. So that's what it really is showing here. Likewise, we compute that second Haar feature. Remember, we looked at two of them. Where is it? Yeah, we looked at two of them. So we compute that second Haar feature also. And you can see again the formula like being applied. And we compute basically that. And that results in again some of these like gray values appear, while the rest of it is all like dark. So now what we want is, we looked at these features, but we want to make sure both of them are satisfied, right, for something to be really passing as a face. So that's why we do AND operation of those two, and we start to see like bulk of the stuff is like gone, but we have some of these like peaks remaining. Right? With these peaks, we'll again do our technique that we've used already multiple times. We'll suppress their like local neighborhoods, and you find basically these couple of like points appear. So these points, what's interesting about them is that as far as those like Haar features, the condition we set for those faces are satisfied, we face should pass. Something else could pass like also, but anything that's not a face should get blocked. So what we have done essentially is, in this case, I handcrafted these like features. So these thresholds being used basically are like computed by hand. So that's why most of the points got eliminated. So you see these thresholds are like handcrafted here. Most of those points got eliminated. In a typical like setting, many large number of points will pass. But see, but very simple technique, we've rejected most of those points as like non-faces. They're not centered on faces, but we got some points selected. But what exactly are we looking at with these points? When I still basically find out. So when I try to draw some rectangles around really those like regions, right? Just as what we were really like seeing, I think in this sheet. No, I think, well, I forgot. So in these really like regions, right? Yeah, in these regions, we're going to take that point and we're going to draw a rectangle around basically that region. So that's what we are going to do next. But this is like a little bit tricky now. How do we do that in Excel? Again, we are using some simple formulas. I'm going to take each point and I'm going to draw a square like around it. Turns out it's not actually very hard, right? So what we have already looked at is a blurring operation. Remember, we did local averaging, which resulted in blurring. And we have also looked at edges operation. So let's look at if I blur it, what happens? I took the same image, I blurred it by a very wide, large rectangle, which is the size of that rectangle, and my points turn into these like little squares. And now what I want to do is we're going to find edges of maybe these ones. That also we have seen a technique already before, even though I'm using a shortcut like formula here. And just with that, finding those edges, we were able to turn those points into these like squares. So let's see what happens if you want to turn, if you want to combine basically those, superimpose those rectangles onto our original image. Right, so I've taken a darkened version of that image and we superimpose those rectangles right here to see what came. So surely we see Mona Lisa's like face has passed in, but we also have some spurious regions coming up. This one is particularly interesting. You see these like what is our very simplistic algorithm is seeing. LE and PA, it's being seen as the eyes because those are darker, and the top and bottom region as well as this nose region ends up becoming brighter. So some of these false positives are showing up. Now, this is what we could do with just two hard features, right? Actually, technically they're called Haar-like features. So what we can do is we'll try to add yet another like hard feature, right? In this case, this is now very much handcrafted. It's made to work for that particular image. I'll later talk about how it is actually done for the real case like scenarios, right? So here I handcrafted this like particular like feature. This is we called Haar-3. We compute that. Now, one curious technique about this one, which was one of the landmark very interesting things from the Paul and Viola Jones like paper, is that these subsequent features that we compute, we don't have to compute for every like region. We already had some basically interesting points show up, and only for those points we have to check whether they're still faces or not. Anything we have rejected as not face, we basically don't have to do anything for it. Right? So that's what we basically like come here for. So we have these like hard features. But in this particular scenario, right, we are computing in Excel, so we compute this AND operation of all three of them. Right? We didn't have to do it, but in Excel, this is like simple enough to keep. This time around, we still see something around this red region, which is not a coincidence, it's because I hand-tuned that Haar-3 feature like for basically that. But everything else we were able to get it off, right? And if we compute that non-maximal suppression, again, same thing as before, we got only 1 point. And we'll repeat our same old technique. We blur it to form our rectangle square. We find the edge, we will see there, and thereby, there you go. We found only one single like face, which is of Mona Lisa. Happening people, this is a demo of face detection happening, just a demo, but happening right within Excel using series of one-liner formulas only. As a reminder, this is still an Excel sheet. Even this rectangle is drawn by changing those numbers in that sheet. You can zoom in and you can see all those like values right there. Right? Now, of course, what we did was we handcrafted these like features for that specific example. In real life, we have faces which have variable skin tones, they have variable sizes, some are far away, some are closer, some are wearing glasses, some not. They're looking in different like directions, different orientations. So in practice, like what happens, we can't basically just use the handcrafted like thresholds. There's a specific algorithm we use to train basically these values, right? It's machine learning technique. right? So all those thresholds as well as like where to position those hard features along the face is all learned by a technique called AdaBoost or some variation they call it. Right? Here's an interesting visualization that's available on YouTube, which shows how it actually like goes on to like work. I strongly recommend you watch basically that. So using some like machine learned like waves, we can go on to actually do hard feature face detection. The particular technique does not work very well in case face is having some mask like we have during COVID times, or some like special basic cases if they are like partly occluded or they are looking too much like elsewhere and so on. But modern neural network techniques basically do work with that pretty well also. So and what we saw was we saw like two-stage like network, two-stage in our like algorithm. First we computed Haar1 and Haar2, and then we added like Haar3. Right? In a typical like scenario, when those like features are machine learned, you might have as many as anywhere from couple hundred to couple thousand of those like features like applied. And besides Haar-like features, there are many other features that have been like made to work also. And likewise, number of stages we just use two. It's not uncommon to go anywhere from like 10 to like 30 stages like that. So having like seen a demo of how face detection could be done in Excel, we will now look at again a toy problem, how to read text out of the images. So this time we start with a zoomed in version of the image just to make our text like larger, and we'll see basically what to do. So far what we had was we had this very simple like Haar-like features where we were just averaging those values out and comparing if some regions are darker than another. So essentially what we are doing is we are multiplying some of these values of +1 type of like weight, some of these values by -1 type of weight, and we're just summing it together. But what if we were allowed to choose a different weight for each pixel? Right? That becomes a little bit like more powerful. In fact, quite more powerful, I would say. So let's look at what could happen. So in this case, there's a different mask chosen where we have plugged in these values. They're like semi-handcrafted, right? But what you are already seeing, there's this E which is like making an appearance over here with these negative values. There are also like some other like cells showing up with like positive values just showing up in green, and a lot of cells which are like just these white, which are very small values. So you've probably already sensed this is time to do something with an E, but we'll see basically what exactly is going on. So what we will do is we will take those values and we'll do pairwise multiplication of those values with a portion of the image. So this is the region of the image I was like we were looking at. In this case, it carries a 2. Right? We just do pairwise multiplication, so values will show up here, and we just sum them together. Right? So very simple. It's essentially just a weighted sum. Nothing more complex than that. So what you will see here is that when the values are happening to be here along that E, if those values are like darker, right? Remember, when there is a 2, those values are darker. Those values will result in more basically like different weight. And if something is showing up in these regions, that will actually get penalized because in uppercase E is not supposed to have like things here. Right? But these other values are completely getting ignored. So in this case, what you see is we computed that weighted sum. It resulted in this like hugely negative value up here. But we will now apply the same operation everywhere. Right? Same operation will be just done like everywhere. Right? So when that weighted sum is applied everywhere, that's called convolution. So you can see basically the sum product. Obviously, sum product is like weighted sum in Excel. Right? It's applied everywhere, and we see something like showing up. Most of it is green, but there are some like tiny red things like appearing over here, not like easily visible. Or I think we can zoom in and really see. Yeah, some things are like appearing over here. You see them here, right? So far what we did is something called convolution, and to do convolution, you're using the same formula as we will in Excel, which fits very naturally like here. But what we're going to do next is that we again want to isolate those like red regions here. So we apply a threshold operation. So I subtracted like some threshold here, 25,000 in this case. And if the value is more than that, I keep that value. But if the value is less than that, we force it to be a 0. So this, some of you who are like who have looked into neural networks, especially modern neural networks, will recognize that as ReLU operation, rectified linear operation. So essentially what we did a convolution followed by this non-linear activation function called ReLU. Essentially what we have done is we have a single convolutional neuron that we have applied over the image. Right? So those who have like looked at deep learning would be like familiar with that convolutional neurons. Right? But this is all there is to it. A single convolutional neuron, this is what it is doing. It's a weighted sum along the local neighborhood, followed by some non-linear like operation, like ReLU in this case. So with that, we like zeroed out all those like other regions. We already have these like red dots like appearing. And there may still be local neighborhood like around those, because if those are more than this 25,000 value, they will still appear. So what we did is local, those non-maximal suppression like again, and we got those like 4 points remaining. Some of you may actually know that this non-maximal suppression is a nonlinear operation already. So technically speaking, this nonlinear activation function was not really required. You could have straight got to that non-maximal suppression, but this was done just to showcase how simple a convolutional like neuron is. But with that, we got these points, and I think I might be seeing a point here too. Right. So with that, let's again use our same old technique that we had before. We blur them to find these like rectangles. We do the edges on them to find our these like again rectangles, and we superimpose them on the top of our original image. And what we see is that it found these like uppercase E's, but it also had a false positive, which is this L. So keep in mind, if this false positive is there because we used very single like neuron. And typical like setting will use lot larger number of like neurons, right, forming a neural network. Deep neural network typically are not necessarily required for just character recognition, but for handwriting and like more complex character recognition, deep neural networks could be used too. Here with a single neuron, we fine tune just to recognize uppercase E's of a given size, oriented vertically. We also had this like false positive. In fact, it turns out I left it on purpose. If you were to basically fine tune these weights a little bit more, you would be able to basically get rid of that like particular false positive like also. So with that, we saw a toy demo of how do we do OCR or on images. Again, like we showed as a simple example with like single characters. But like if you use multiple neurons, you can actually go on to use the same technique to find multiple characters. So we learned basically a couple different algorithms, right? Within Excel, we went from finding points, lines, edges. We looked at one area-related algorithm, and we looked at one more powerful algorithm for neural networks, which can do lines and corners like as well. So our thought basically here was to show you, right, within Excel using simple formulas, how some simple algorithms for computer vision work, and you're trying to identify these different geometric shapes there, right, right there. Now it turns out while we came up with this cool technique to show this computer vision stuff working right within Excel, we later discovered there have been some prior works in which people have used images like within Excel. There have been some prior works even doing things like ray tracing and 3D engine right in Excel. You can follow these URLs to look for more. To the best of my knowledge, though, we are the first ones to like try a computer vision type of thing in Excel. There's some more stuff. I think there have been some demos showing deep neural networks in Excel also, and there will be some links that you can like find when you saw it. So with that, we come to end of our close to our end of our session. We saw what this computer vision did into this BMX.Excel itself. So again, just a reminder, all this Excel file as well as some other resources are available for you to download under open source at this particular link. We'll put that as a comment on the video link also. And you will see some frequently asked questions also on those resources. Special thanks to Amazon and the team for making it open source to be able to spread this knowledge to all of you. We have been approached by many people who are new to computer vision who found this session very useful. So thanks again to Amazon for making it open. I think this we already covered. So with that, we'll questions are we're not taking in this particular session, but as we mentioned, you are free to reach me offline. Plus, as well as in our that link we shared, there are some questions already answered. And with that, we come to our end. I'd like to thank Manish Kumar who made the artwork for this session, as well as Darby who's coordinated this session for this recording. Thanks to all of you.